spend a few minutes reviewing what we did last week on forces. You guys all remember, of course, that a force is a push or a pull. But what you might not remember are the two things that a force can do, the two effects that a force can have on an object. Who remembers what one of those effects are? Yeah, what's one of them? Good, it can accelerate the object, and that means it can cause it to speed up, it can cause it to slow down, it can cause it to change direction. All of those things fit within accelerate an object. What's the other thing that a force can do to an object besides accelerate it? Yep. It can deform the object. It can change its shape. Okay. It can squish it or it can stretch it. It can deform the object. Is there ever a situation where it can do both? Change the shape and deform the object? Sure, there's tons of them, right? Bounce a basketball. What happens when that basketball hits the ground? Well, the basketball accelerates, right? It slows down, and then when it stops, it speeds up in the opposite direction. If you were to take a slow motion video of the basketball, what would you find about the shape of the basketball? It would squish, right? It would change shape. So the basketball is being deformed, and the basketball is changing direction, and the basketball is speeding up, and the basketball is slowing down, all at the same time. So the force is doing all of those things, accelerating the object and changing the shape of the object, deforming the object. Make sense? All right. We talked about two more terms. One was static equilibrium, and the other one was translational equilibrium. Who remembers what the term equilibrium means? That's where we got to start with this, right? Equilibrium means, Matt? Balance, good. Static means still balance. So if an object is undergoing a static equilibrium, if it's in static equilibrium, then what do we say about that object? It's not moving? Yeah, it's not moving, and something's balanced. What is it that's balanced on it? Yep, Oliver? The forces. The forces are balanced. So if an object is in static equilibrium, it's at rest with balanced forces. Now, what's going to happen to that object if it's in static equilibrium? What's going to happen to it if it's at rest with balanced forces acting on it? It's going to stay at rest forever, right? Until there's an unbalanced force that acts on it, until it's not in static equilibrium anymore. An object in static equilibrium will remain at rest forever and ever and ever with balanced forces acting on it until something is unbalanced. What about translational equilibrium? Translational balance. What's that word translational mean to us? Moving balance. Okay, so now we're talking about an object that's moving with balanced forces acting on it. What do we know about that object if it's moving and has balanced forces acting on it? Connor, was your hand going up there? No? Can you answer that? What's going to happen to the object that's moving if there's balanced forces acting on it? Good. It's going to keep moving in a straight line at a constant speed unless something unbalanced acts on it. So both of these are, in one respect, opposites to one another, right? One's at rest, one's moving. One stays at rest, one stays moving. So in that sense, opposite. But in another respect, they're exactly the same. Which I mean by that, an object at rest stays at rest, an object in motion stays in motion. In other words, whatever the object's doing, it wants to keep doing. If it's at rest, it wants to remain at rest. If it's in motion, it wants to stay in motion. What's the term that we assign to that? That little idea that an object wants to keep doing what it's doing. It's an I word. Inertia. The tendency of an object to resist a change in motion. The tendency of an object to keep doing what it's doing. Now, what's inertia related to? What affects inertia? There's only one thing. The mass. The heavier an object is, the more inertia it has. So, if an object's in static equilibrium, it's going to stay there. An object with more mass has a higher tendency to stay at rest, or an object with higher mass has a higher tendency to stay in motion, whatever it's doing now, right? Has a higher tendency to keep doing whatever it's doing, all right? Well, today I want to go a little bit further and not so much talk about forces in balance. in objects that keep doing what they're doing, but rather I want to talk about objects that experience net forces or unbalanced forces. In other words, objects that are going to accelerate. There are two things that affect acceleration, two things that acceleration depends upon. Anybody want to take a stab at what one of those things are? I want you to picture something in your mind. Okay, I want you to picture something accelerating, something speeding up. And I want you to think about what affects that thing that speeds up. Cody, what object are you thinking of right now that's going to speed up? Oh, see, he wasn't ready. He wasn't ready for that question. He wasn't thinking of something. See, everybody's going to be thinking of something. Everybody think of something that is speeding up. Okay, Carson, what are you thinking of that's speeding up? A car? Okay, what kind of car? Think of it in detail. I want you to see it. Picture it. It's a movie. It's a 3D movie in high def. Okay, Brandon, what are you thinking about that's speeding up? A roller coaster. What's the color of the roller coaster? A wooden one. Okay. Okay. How many cars on the wooden roller coaster, Brandon? Okay. Okay. Brandon's passing so far. Brandon, what affects the acceleration of that brown wooden roller coaster? Okay, the mass of it. Let's go with one thing at a time. The mass of the wooden roller coaster. How does that affect it? If you have more mass on the roller coaster, how does that affect the acceleration? Does it make it higher or lower? Let's think of another example using mass. You've got a smart car and you've got a semi-truck. And you push on both of them with the same force. Which one accelerates quicker? The smart car. How come? Because it has lower mass and less inertia. Good. So the more the mass, the less the acceleration, not the more. We're going to say that A is related to the inverse of the mass. Have you ever seen that expression there? That little Greek letter alpha? It means proportional to or related to. The acceleration is related to the inverse of mass. In other words, as mass goes up by a factor of 2, A goes down by a factor of 2. As mass gets quadrupled, A goes down by a factor of 4. As mass goes down by a factor of 3, then acceleration goes up by a factor of 3. They're inversely related to each other. What else does it depend upon? Yep. No, not so much gravity. It can depend upon gravity, but I want to make I want to use that as a kind of open that to a looser term, like a more general term than just gravity. Again, similar to gravity in the sense that I want to make it a more umbrella term that encompasses both of those things. Force. Okay, you can have a force of air resistance, a force of gravity. Okay, in general, it applies or it's related to the force, and that's a direct relationship. Meaning that as force goes up by a factor of 14, then acceleration goes up by a factor of 14, right? Mass goes up, acceleration goes down. Force goes up, acceleration goes up. Direct relationship and inverse relationship. Isaac Newton put both of those together in what we call his second law. Newton's second law says two things, really. We'll put them together, actually. We'll put them together as one. It says the acceleration of an object is directly related to what? You fill in the blank there. It's directly related to what? It's not inversely related to this. It's directly related to the net force, yes. It means that as F goes up, acceleration goes up. As F goes down, acceleration goes down. If F is to the right, then acceleration is to the right. If F is to the left, then acceleration is to the left. Acceleration of an object is directly related to the net force. In other words, A is related to F. If we were to plot that as a graph, we would see that it would be a straight line graph if it's a direct relationship. But it's also inversely related to what's the word I'm looking for here to fill in the blank? Yep, the mass. It's inversely related to the mass. If you write that out as an expression, it looks like this. A is proportional to 1 over m. And if we were to plot a graph of that, A versus m, instead of A versus F, it would look like this. A lot of people think, by the way, that A versus m should look like this if it's an inverse relationship. That's not an inverse relationship. That's a direct relationship with a negative slope. Right? It's still a straight line. That's a direct relationship every time you see a straight line. It's just a negative slope, that's all. An inverse relationship, 1 over m, as opposed to A is proportional to negative m, 1 over m looks like this. This is A is proportional to negative m, which of course is incorrect. We can combine these two ideas relating force to acceleration and mass to acceleration and write it out as one equation. A is equal to F over m. That's Newton's second law. This is the way we usually see it written, however. And this is the way that it appears on our data sheet. F is equal to m times A. Whenever you see that, remember that this is Newton's second law. I really should put a subscript here for force. Net force. Not just any force, but net force. If there's 3 forces acting on an object, it's not one of the forces that we're concerned with, it's the 3 combined that we're concerned with, the net force, the unbalanced force. Let's see what we can do with an example on page 149. It says a lacrosse player exerts an average net horizontal force of 2.8 newtons forward on a 0.14 kilogram lacrosse ball while running with it in the net net of a stick. Calculate the average horizontal acceleration of the ball while in contact with the lacrosse net. This is a problem that we know is a Newton's second law problem, right? This is a problem where we're dealing with a force that's proportional to the acceleration. We want to find the acceleration. So let's write down some givens, use Newton's second law to solve it. F is equal to 2.8 newtons, and it's forward. We'll define positive as forward. The mass is 0.14 kilograms. We want to find the acceleration. We're just going to use that F is equal to ma equation. Or A is equal to F over m. And say it's 2.8 newtons divided by 0.14. They make this question easy enough that we can actually divide those two in our heads here. 28 divided by 0.14 is going to be 20. The units would be newtons per kilogram. That looks a little odd. That's fine. Newtons per kilogram works there. But you could also say 20 meters per second squared. I mean, Newton per kilogram is exactly the same thing as a meter per second squared. So whatever you're comfortable with at that point. Okay, let's spend a few minutes at your desks working on the questions on 149, please. All right, if those are good, let's have a look at one more question. I want you to try this one yourself. It's an example, but I want you to try it yourself, and then we'll take a look at it as a group when you're finished going over it yourself. All right, when you look at this question, it's almost like two thoughts that come to mind. Newton's second law, you're looking for a force that's required to accelerate at a certain rate, but we don't know what the acceleration is. Yeah, that's a group B problem, right, when we want to find an acceleration. So let's use Newton's second law and all those group B equations that we learned in our last unit to solve this question. Let's write down some givens first, though. Let's say m is equal to 1,000 kilograms. Let's say VI is 72 kilometers per hour, which if you multiply that by 1,000 divided by 3,600, it gives me 20 meters per second. We're going to say that VF is equal to 0 because it comes to a stop. Time is 10 seconds. And we're looking for the net force here. much force is required to stop the car. All right, let's write down Newton's second law. The only thing that can get us force at this point, F is equal to m times A, but we don't know what A is. So let's go over to the side here and do a group B equation. Use a group B equation to solve this. Let's say A is equal to delta V over delta T. Delta V is 20 minus, I was going to say 20 minus 0. It should be 0 minus 20 over the time of 10 seconds. So we get negative 2.0 meters per second squared, which we plug back into here. 1,000 kilograms times negative 2.0 meters per second squared. For the right number of digits, this is 4, this is 2, this is 2. Final answer should be 2 digits. Should be negative 2.0 times 10 to the 3 newtons. How many people got that? How many people said it was negative? It should be negative, right? The acceleration is negative because it's slowing down, and the force is in the same direction as the acceleration, so it's got to be negative as well. Okay, the only answer we take here is negative 2.0 times 10 to the 3 newtons.